Now in this lesson, we are going to learn about Einstein's photoelectric equation. Einstein's photoelectric equation is E equal to K max plus work function. This is nothing but conservation of energy. Some light is falling on a metal surface. This energy is now coming in packets. That's Einstein's photon theory. So energy in a light beam is coming as a packet of energy. This electron sitting here on the surface absorbs the entire energy. A part of that energy is used to overcome work function, and remaining energy becomes K max of photoelectrons. Now if electron is inside the metal, then it will take some more energy to come to the surface. So energy of the electron can be anything from 0 to K max. Remember, in photoelectric effect, the energy of a photoelectron varies from 0 to K max. So this energy is falling on the electron. The electron absorbs the entire photon, a particle of energy it absorbs, a packet of energy. A part of that energy is used to overcome work function, and the remaining energy becomes K max. That happens in the best case when the electron is on the surface. If electron is on the side, waste some energy to come to the surface, and then the energy will be less than K max. So energy of photoelectrons ranges from 0 to K max. So this is Einstein's photoelectric equation. From this equation, we get K max is equal to E minus work function. E is the energy of the photon, and work function varies from metal to metal. This is the minimum energy that needs to be given to an electron to make it come out of the metal surface. Now K max is E minus work function from this equation. E is the energy of the photon. So K max becomes HF minus work function. This is Einstein's photoelectric equation. This has come from simple conservation of energy. Electron sitting on the metal surface absorbs an entire packet of energy, that is a photon at one time. A part of that energy is used to overcome work function, and the remaining energy becomes K max of photoelectrons, that is in the best case. Otherwise the energy can range from 0 to K max. Now we will see how this equation overcomes the three objections or three shortcomings or three problems that we found with the wave theory of light. First problem, according to wave theory, K max should depend on intensity, but actually K max depends on frequency. Now look at this equation. K max clearly depends on frequency. So therefore, that problem is solved. As per this equation, K max depends on frequency, not intensity of light. Second problem, according to wave theory, photoelectric effect should occur for any frequency of light if the intensity is large enough. Now look here, for the electron to come out, K max has to be more than 0. Kinetic energy cannot be 0 for the electron to come out. So K max is more than equal to 0. That means HF minus work function is more than equal to 0. Solve this. Frequency should be more than equal to work function by H. That we call it threshold frequency. So for the electron to come out, the frequency of light has to be more than threshold frequency. If F is less than F0, the electron cannot come out as per this. and that matches experimental observations. Right? Simple. Now, third problem, absence of time lag. As per wave theory, the electron should take time to absorb the required energy and then come out. But actually, the electron comes out immediately. Now energy is coming as a packet, not as a continuous flow. And the electron absorbs the entire packet of energy at one go. And therefore, it can come out immediately. Like suppose you are eating small particles. It will take time for you to eat some reasonable quantity. And you eat a laddu. You can eat it immediately. So now, it is a packet of energy that is coming to the electron. That's why the electron can come out immediately. Other way to understand this, suppose this is a tree and this is same tree. Okay, here you are watering with the help of a spray. So spray of water is going. So it will take time to water the plant. Here you have got a bucket of water. This bucket you can empty at one go and the tree is watered. So this is the difference. In the wave theory, the energy is coming continuously. It takes time for the electron to come out. But there, in particle theory, it is coming as a packet. So electron absorbs the entire packet of energy. Therefore, it can come out immediately. So this is how Einstein's photon theory explains photoelectric effect. All the three problems that the wave theory had in explaining photoelectric effect are taken care of by Einstein's photon theory. Einstein's photon theory is nothing but conservation of energy. When photons of energy more than equal to work function fall on a metal surface, electrons are liberated from that surface. When photons of energy HF greater than equal to work function fall on an electron, the electron absorbs the entire photon and a part of that energy is used to overcome work function and the remaining energy becomes Kmax in the best possible case. So Kmax plus work function is equal to the energy of the photon. So from this equation, we get Kmax equal to HF minus work function. And it can be clearly seen that Kmax depends on frequency, not intensity. And that matches experimental observations. For the electron to come out, Kmax has to be more than equal to 0. That is HF minus work function has to be more than equal to 0. From here we get frequency to be more than equal to work function by Planck's constant, and that is threshold frequency. Therefore, if frequency is less than threshold frequency, photoelectric effect will not occur. Third one, absence of time lag. Now a packet of energy is coming. So electron absorbs the entire photon and it can come out immediately. It is not a continuous flow of energy, it is a packet of energy that is hitting an electron, therefore there is no time lag. In this lesson, we are going to learn about the graphs that come from Einstein's photoelectric equation. We know that the energy of a photon is equal to the Kmax of the photoelectrons plus the work function. Right? When photons of energy E equal to HF more than the work function of that metal fall on a metal surface, the electron absorbs an entire photon. A part of that energy is used to overcome work function and remaining becomes Kmax. So from here we get Kmax is equal to HF minus work function because E equal to HF. Right? Now Kmax is HF minus work function. This is the equation. This is like y equal to mx plus c. We plot Kmax against frequency, we will get a straight line. and the straight line will have negative y-intercept. Slope is positive, but the y-intercept is negative. So here you have got Kmax and here you have got frequency. So we get a series of parallel lines whose y-intercept is minus of work function. So this is for a different work function Wt by E. And the slope is equal to Planck's constant. Slope of these two lines is Planck's constant. Now we cannot measure Kmax directly in the lab. How do you measure Kmax? What do you use? Use stopping potential. Stopping potential is a measure of Kmax. So now look at this equation again. What is Kmax equal to? E times stopping potential. This will be equal to Hf minus work function, and therefore stopping potential is H by E is the charge of electron multiplied by frequency minus work function by E. Again this is like y equal to mx plus c. So plot stopping potential against frequency. Again you will get a straight line. Slope will be h by e and the y-intercept will be minus w by e. So what do you get here? So this is now stopping potential. This is frequency. Slope is h by e and the y-intercept here is work function by charge of electron. These two graphs are very important. Both of them come from Einstein's photoelectric equation. E equal to Kmax plus work function. So Kmax becomes E minus work function. E is Hf, the energy of a photon, a packet of light, a packet of energy, right? A particle of light. So from that equation we get Kmax equal to Hf minus work function. When Kmax is plotted against frequency, we get a series of parallel lines whose slope is Planck's constant and whose y-intercept is negative of work function. Remember that. When we plot stopping potential against frequency, again we get a series of parallel lines whose slope is Planck's constant by charge of electron and whose y-intercept is work function by charge of electron. So this is what is very important for us to remember in Einstein's photoelectric equation.